right, this is the very last BC lesson, and we're going to talk about the calculus of polar curves. Okay, and so the very first thing I want you to do for fun is we're going to graph this wild and crazy polar curve. This wild and crazy polar curve, let me hide this, has an equation that is this equation. And what's interesting about this is a period is 2 pi over b. So this period isn't like the ones that we're used to in honors pre-cal. So that's why we get this effect. But let's graph it on the calculator and see what we get. Well, wait a minute. We have to be in a different mode because this is r of theta. So we have to change our mode. We have to change our mode from parametric mode to, there we go, we're going to use number 3, which is polar mode. I'm going to press enter. Okay, now we're in polar mode. We're going to go to y equals. And, it really shouldn't be y equals, right? It should be r equals. But anyway, you notice that now we have r. And so when I type in r, let's see what happens. We want to type in 2 sine, so a second, sine of 2.15 theta. Now, where do I find theta? Well, on our calculator, our theta is by the pi. So we're going to do diamond theta, which is right here, and then close the parentheses, and we're going to make sure our calculator is in radians because calculus is rad, and you'll notice that mine is indeed in radians. And I'm also going to change the window. So let's go diamond window, and you're going to see that now you have a theta min and a theta max, and I'm going to change my theta max to 14 times pi. And I'm going to press enter. And the pedal length is going to be 2. So I think that negative 10 to 10 would be all right. So let's see what happens when we hit graph. So diamond graph. Mine's pretty small. How about yours? Okay, so we're going to change the window. Mine's still busy because it's going all the way to 14 pi. Okay, diamond window. Let's change this to F2 zoom. I wonder if zoom trig will work. Makes it bigger. But we can probably do better. Let's do diamond window. Let's change it from, let's do negative 5 to 5. And that's better. We can see it better now. Anyway, I just wanted to show you how to graph a polar curve on your calculator on your 89 because we haven't done that yet with a wild and crazy period. So that was kind of fun. All right, let's move along. Now, these notes are guided, but I'm just going to go over this quickly and then we'll do some examples. Oops, sorry about that. Calculator survived, thank goodness. All right, so to find the slope of a polar curve, given that we have r as a function of theta, and knowing that x equals r cosine theta and y equals r cosine theta, this is what you do. It's like parametrics, except that instead of a t, we're going to use theta. And dy dx, which is always the slope, is equal to dy d theta over dx d theta. And this would be equal to, well, this is dy d theta. Well, what is y? Well, y is r sine theta. So what do I have to do? I have to use the product rule because I'm taking the derivative of this right here is y, and this right here is x. And we have to use a product rule over here. So we do first d second plus second d first, which, is backwards here. But anyway, you do the same thing in the denominator. Okay, now I don't memorize this formula. I just take the derivative of whatever I have here. Okay, so it's you're going to use the product rule and knowing that y is r sine theta and x is r cosine theta, and then you use product rule. All right, so let's do an example. I have an example right here ready to go. Okay, we're going to find dy dx for the polar curve r equals 1 cosine theta. All right, so when I do this, the first thing I do is I say, well, I know x is equal to r cosine theta, and y is equal to r sine theta, two of the pillars of polars. Okay, and I need dx d theta. Well, dx d theta is just the product rule. Well, hold on. I'm sorry. I'm gonna do one more step so you can see. So x is what? What is r? R is a function of theta, so it's gonna be 1 minus cosine theta times cosine theta. And y is going to equal r, which is 1 minus cosine theta times sine theta. All right. And dy dx is equal to dy d theta over dx d theta. All right, so now I'm going to do my little product rule here, right? For dy d theta, I have to go to y, and it's going to be first, which is 1 minus cosine theta, d second, which is cosine theta, plus second, which is sine theta, d first, which is the derivative of 1 minus cosine theta, which is just sine theta, right? Because the derivative of cosine is negative sine, and that's a negative. So, all right, all over. And I'm going to do the same thing with x now, except I'm going to use the product rule. So it'll be first, 1 minus cosine theta, d second, which is negative sine theta, plus second, which is cosine theta, times the derivative of the first, which is, again, the derivative of negative cosine is a positive sine theta. All right, now it's tempting to cross these out, but we can't. We just can't because they're part of this addition, and they're not factors. Okay, so let's simplify this a bit. We're going to get cosine theta minus cosine squared theta plus sine squared theta. Okay, all over negative sine theta plus, that would be sine theta cosine theta, because it's positive, plus sine theta cosine theta. So let's extend my division bar there. Okay, now this really here is cosine theta, and I could do minus cosine squared theta minus sine squared theta. Now I did that for a reason so that you could see that that's an identity here. And then this one here is negative sine theta plus, well, there's two of these here, plus 2 sine theta cosine theta, which is also an identity. So this turns out to be cosine theta minus cosine of the double angle over negative sine theta plus sine of the double angle. And that would be dy dx. And if ever I wanted the slope at some angle, I could figure out what the slope is at an angle. Okay, and now I have taken the liberty of graphing r equals 1 minus cosine theta, as you can see here. And you see this is a cardioid, and this is a curve. This is a curve, and slopes need to be found. So now we have the expression for the slope. Oops. We have the expression for the slope. I don't know if it's going to minimize it quite as much as I'd like. Anyway, we have the equation for the slope. And I could find the slope when theta equals pi over 2. So let's find the slope when theta is pi over 2. So we'll find dy dx when theta equals pi over 2. Okay, Well, dy dx from theta is pi over 2. Let's figure this out. That means I'm going to put pi over 2 in here. So this would be the cosine of pi over 2 minus the cosine of, well, when I plug pi over 2 in here, I get pi over negative sine of pi over 2 plus the sine of, well, when I plug in pi over 2 here, I get pi. Okay, this would be dy dx equals, all right, and the cosine of pi over 2, thankfully, is 0. And then this turns out to be 1 here over, the sine of pi over 2 is 1, so this is negative 1 because the sine of pi is 0. So the slope is negative 1. Well, it looks like the slope of the tangent, whoops, I'm sorry. It looks like the slope of the tangent line here would be negative 1. But let's find out what the tangent line is at 1. So I need a point. So I need x at pi over 2. So x is equal to r cosine theta. So it's going to be 1 minus the cosine of pi over 2 times the cosine of pi over 2. And all I'm doing is remembering that x is equal to r cosine theta, right? Which is equal to 1 minus cosine theta times cosine theta. Right? That's all I did. And what happens when I do this calculation? I get cosine of pi over 2, thankfully, is 0. So this just turns out to be 0. So let's figure out what y is. Y at x equals pi over 2. I should write it similarly. Well, we know y equals r cosine, r sine theta, sorry. R sine theta, and that's equal to 1 minus cosine theta times the sine of theta. And when I plug it in, I get y equals 1 minus the cosine of pi over 2 times the sine of pi over 2. Well, we already know the cosine of pi over 2 is 0 and the sine of pi over 2 is 1. So this turns out to be 1. So the point is 0, 1, and dy dx is equal to negative 1. So the tangent line to r equals 1 minus cosine theta at theta equals pi over 2 is going to be y minus 1 equals negative times x minus 0. Okay, and let's prove it to ourselves because we can. We can say y minus 1 equals negative x minus 0. And sure enough, you can see that I have a nice little point there, tangent to the curve at theta equals pi over 2, which is pretty cool. The other interesting things about trying to find out about slopes of cardioid around the cardioid function is it's nice to know when you have horizontal tangents and vertical tangents, okay? So I'm going to grab another piece of paper here, and we're going to find out when the tangent line to the same curve is. So this is like a part A here, finding the slope, right, of the function and finding it a tangent line to the curve at that theta. Okay? But now what we're going to do is we're going to figure out when we have horizontal tangent lines, given that r equals our function still, 1 minus cosine theta, we want to find the horizontal tangent lines. To the curve. Okay, so to find the horizontal tangent lines to the curve, I need dy dx. And as we recall, dy dx was, bringing the paper back, cosine theta minus cosine 2 theta over negative sine theta plus sine 2 theta. All right, so that was my derivative. Horizontal tangent lines occur when the numerator is equal to 0. So that's when this is equal to 0. So I'm going to turn and put cosine of theta minus cosine 2 theta equal to 0. Now, I have a cosine here, so I'm going to use the all cosine version of the double angle. So this will be cosine of theta minus 2 cosine theta squared theta minus 1 equals 0. And I'm going to multiply it all out here. Cosine theta minus 2 cosine squared theta plus 1 equals 0. And then I'm going to move everything to the right side, if that's all right with you guys, and make this 2 cosine squared theta minus cosine theta minus 1 equals 0. And lucky for us, I do believe this factors. I should have worked it ahead of time, but of course time is of the essence. And then this will be 1 and 1, and I have to have a negative here. Let's see if I moved it over right. That's positive, negative, negative, right? Okay. So this 2, 1 has to be negative. This factor, right, 2 cosine theta has to be negative to get a negative cosine in the middle. So those are our two options. And I know there are going to be two options because I have one up here and I have one right here. Okay, so setting them equal to 0, we're going to say 2 cosine theta plus 1 equals 0, or cosine of theta equals, minus 1 equals 0. And if I'm solving this, I get 2 cosine theta equals negative 1. Cosine theta equals negative 1/2. What quadrants is the cosine negative? Well, it happens to be quadrants 2 and 3. And what's alpha? Yes, alpha is pi over 3. So my thetas are going to be theta equals 2 pi over 3, because that's a pi over 3 angle in quadrant 2, and then 4 pi over 3, which would be the pi over 3 angle in quadrant 3. And then cosine theta equals 1. Where does that happen? Well, that happens when we're right here, which is theta equals 0 or 2 pi or so on and so on, because we can go around many times. Okay, so what would the tangent line be there? Well, I need what y is, don't I? Because horizontal tangent lines have y equals, right? So I need the y. Knowing that y equals 1 minus cosine theta times sine theta. I'm 1 minus cosine theta because this is r cosine theta. I'm going to go such that theta equals 2 pi over 3. And what happens here is I get 1 minus the cosine of 2 pi over 3, which is negative 1/2. And the sine of 2 pi over 3 is root 3 over 2. And so this is going to be 1 plus 1/2, which is 3/2, which would be 3/2 times root 3 over 2, which is going to be 3 root 3 over 4. And let's see if that works. I'll know soon enough. 3 square root 3 divided by 4. Oh, yay! It worked! It worked! It worked! There it is. And then if I did 4 pi over 3, so y equals, what's the equation of the horizontal tangent? What's going to be y equals 3 root 3 over 4. That's the equation of the horizontal tangent line. And then y equals 1 minus cosine theta sine theta, such that theta equals 4 pi over 3. What happens when we plug in 4 pi over 3? Well, the cosine is still negative 1/2, so we're going to get 1 minus 1/2 times the sine. Now the sine is now negative because it's in quadrant 3. And then this is just going to be negative 3 root 3 over 4. So my tangent line is going to be y equals negative 3 root 3 over 4. And we're about to see if we're correct, because I'm going to copy and paste. Control C, Control V, and put a negative out in front. And sure enough, you see how it's tangent there? And then there's one here at 0. And I want you to see that that looks like it's approaching a zero tangent line, and it would also be a zero tangent line there, okay? I'm not going to do that one. All right. Having said that, we have found the horizontal tangent lines. What also needs to be found? I heard it from the back. The vertical tangent lines to the curve. So when are those going to occur? Well, Mrs. Muller, vertical tangent lines occur when the denominator is equal to 0 of the derivative. Finding vertical tangent lines. 2r equals 1 minus cosine theta. Okay, recalling that dy dx was equal to, I forgot already. I'm looking cosine theta minus cosine 2 theta over negative sine theta plus sine 2 theta. And we want to know when this is undefined, because that's when we're going to have vertical tangent lines. All right, so that's going to be undefined when the denominator is equal to 0. So that's going to be negative sine theta plus sine 2 theta is equal to 0. And I'm going to use my knowledge of the trig identity of sine of the double angle. So negative sine theta plus 2 sine theta cosine theta equals 0. I'm going to factor out a sine theta, and I'm going to be left with negative 1 plus 2 cosine theta equals 0. Okay, and so now we're going to have two equations. We're going to have sine theta equals 0, and we're going to have negative 1 plus 2 cosine theta equals 0. And so sine theta equals 0 here and here on the x-axis, so that means theta. Theta is going to equal 0, pi, 2 pi, any of those, and so on, right? And then I'm going to have 2 cosine theta equals 1, cosine theta equals 1/2. Cosine's positive in quadrants, 1 and 4. And so alpha is, again, pi over 3. And theta is going to either equal pi over 3, or we could say negative pi over 3. Or we could say pi over 3. Okay? So let's find out what the equations are for vertical tangent lines. Right now, vertical tangent lines are always x equals. And we know that x happens to be r cosine theta, where r is equal to 1 minus cosine theta times cosine theta. And we're going to go such that theta equals pi over 3. So what happens when I let theta equal pi over 3? We get 1 minus 1/2 times the cosine of pi over 3, which is 1/2. So this is going to be 1/2 times 1/2, which is 1/4. Okay, and let's see if that works. X equals 1 divided by 4. Sure enough. And you see how this is going to be the same? So it's going to be the same for each one of these. You've got two verticals here that touch the cardioid in the same spot. So x equals 1/4 would work for both of the vertical tangent lines on the right of the curve. And then we're going to we're going to say x such that the sine or the angle is, I'm sorry, I shouldn't use sine here, I should use cosine. Such that we're going to let's let x equal 0. So what happens at 0? Well, I get 1 minus 1, because the cosine of 0 is 1, times 1, which is 0. So this equals 0. So that's not undefined, is it? No, it's at x equals 0. But this is extraneous. Because when x is 0, it doesn't look like I got a vertical tangent there. But let's see what happens when when theta is pi. Oops, I'm sorry, I'm going to put theta here. Such that this is theta equals 0, theta equals pi. I get 1 minus a minus 1 times a negative 1. So this is equal to negative 2. So let's see what happens. Is my line at x equals negative 2? Yes. You see how that works. Okay, so at x equals negative 2, sorry, I have another vertical tangent. Okay, so the cardioid has vertical tangents in 3 spots. Okay, so the most complicated thing I think about finding tangent lines and the slopes to curves is, first of all, slopes to curves require you to figure out what x and y are ahead of time because it's r cosine theta and r sine theta. And then when you find the dy dx, you have to use the product rule because it's a function of theta times a function of theta. Then secondarily, when you're finding the point that you are going to be tangent to, and you know x is r cosine theta, you have to actually figure out what the point is, plugging in theta into r and to cosine theta to figure out what point you're at. So that's the thing that makes that a little bit difficult, but it's definitely doable and very easy. The second thing we do with polar curves is we have to find the area inside a polar graph. Okay, now in rectangular curves, we're finding the area between the curves, under the curve. So I'm going to draw a just slight example. This is what we're used to. We're used to having some function where I am a function of x, and I'm trying to find the area beneath the curve. And what did we do when we added this up? We added a bunch of rectangular areas up, which were lengths times widths. Right? And it would be the integral from a to b of f of x dx, because this was the length and this was the width. So we were adding up rectangular areas. But inside a polar graph, what we're going to be doing instead is we're going to be sweeping out sectors of a circle. Well, what is a sector of a circle? A sector of a circle, I'm not very good at drawing circles, but here's my best shot. Here's my circle. Okay, I'm going to be sweeping out sectors, where I'm going to let r equal a certain amount. I'm going to be sweeping out sectors. And they turn out to be, if theta is really small, so small, you can almost not distinguish it between a sector, which has a curvy edge, and a triangle, which has a straighter edge. Okay, because it's locally linear. When you zoom in and you zoom in and you zoom in and you zoom in, it looks like a line instead of a curve. Okay, and that is going to be, its length is going to be r times d theta, because the length, arc length, let's think about what arc length is, right? That's S equals r theta. Right? And so if I have a sector here, I have a sector, its radius is r, and this is the arc length here, which would be r times theta. But theta is really small, and so I'm going to treat it like a triangle, and it's going to be 1/2 its base, which is r d theta, times its height, which is r. And so I get the area of one slice, and slice of pie, right? One triangular slice, and that's the difference between area under a rectangular curve and an area inside a polar curve, is that we're going to sweep out a triangle, and its area is going to be 1/2 its base, which is r d theta, which is just the arc length. It's a very small piece of the arc length, times the height, which is r, the radius. And then you get 1/2 r squared d theta. But if I wanted to add them all up, all the triangular areas, what am I going to do? I'm going to integrate from alpha to beta. Alpha and beta are just fancy names of saying angles. 1/2 r squared d theta. Now, I like to also write this as 1/2 times the integral from alpha to beta because 1/2 is a constant and we can pull that out in front. Okay? All right, so let's do an example. All right, here's my example. We are going to find the area enclosed by r equals 2 plus cosine theta. And remembering that r equals 2 plus 2 cosine theta, if I were distributed to 2, this is a cardioid, right? And we think about that curve, it's a cardioid. And the cosine's positive, so the large part of the cardioid is going to be on the right side. And when theta is 0, cosine of 0 is 1, so I'm going to go out here radially 4. And when theta is pi over 2, cosine is 0, so it's going to go to 2. So it's 4, 2, and then it's going to go to the pole when cosine is at pi. So it's going to, go to 0, and then it's symmetric, so it's going to bounce off and do this. So that's our cardioid. And I want to find the area enclosed by the cardioid. Okay, so we knew that this is 0 rotation, and this was pi over 2, and this is pi. So to get all of it, what do I have to do? Well, I have to integrate from 0 to 2 pi. Okay, or I could integrate from 0 to pi and use symmetry as my friend. What would you like to do? Well, we'll probably use symmetry here, but what is the formula? The formula, because r, this is a polar curve, it's going to be the area is equal to the integral from 0 to 2 pi, and I'm going to bring the 1/2 out here, of r squared, which is 2 times 1 plus cosine theta, quantity squared d theta. Now we can go from 0 to pi if you like to get use symmetry. So let's do that. So we're using symmetry. What do? We say area is going to equal 2 times that, which would just be the area from 0 to pi, because the 2's cancel. And the only way we can do this is to multiply it out. So I'm going to bring the 4 out in front, because I square the 2 and I get 4. And then I have to multiply this out. So I'm going to go 1 plus 2 cosine theta plus cosine squared theta d theta. Okay, now I can integrate the 1 and the 2 cosine theta very easily, but I have to use the power reducing formula for cosine. So let's do that. We say area equals 4 times the integral from 0 to pi of 1 plus 2 cosine theta plus 1/2 times 1 plus cosine of the double angle of theta, d theta. Right, because cosine is plus and sine is negative when you're doing integrating squares. Okay, so let's simplify that expression some. We get the integral from 0 to pi of 1 plus, now when I multiply the 1/2 in here, we get cosine theta, plus 1/2. So I'm going to change this, if that's all right with you, to 3 halves, right? Because that's going to be 1 plus 1/2. And then this is, I'm sorry, I left the 2 off of here. 2 cosine theta plus cosine double angle d theta. All right, now, so what happens when we integrate that? Well, we get 4 times 3 over 2 theta plus 2 sine theta, because the antiderivative of cosine is sine, plus sine 2 theta over 2, such that we're going from 0 to pi. Okay, so we're going to evaluate that by plugging in pi. Well, the sine of pi and the sine of 2 pi is 0, so that's really nice. So we're going to get 12 pi over 2, which is 6 pi. And then when I plug 0 in, this theta goes away. Sine of 0 is 0, sine of 0 is 0. So we get 6 pi units squared. So we just found our first polar area. Woohoo! which is very, very cool. And what happens when we find the area is that we're sweeping it out. So we're adding up all of these triangles, these mini triangles that are behaving like sectors. Okay, so it's no longer the area under the curve. It's the area inside the curve. So it's not under, it's inside. And we're sweeping out radially swaths of area versus area between, the function and the x-axis. And that's a key difference. Okay, all right. Well, what happens if we have more than one curve? Oh no, yikes. And we have two curves. Well, what happens is we have to take we subtract the bigger curves triangle from the littler curves triangle, and it's just outer squared minus inner squared. Okay. All right. So you need to do some of the homework to practice that. All right. But I'm also going to do to find the area inside a petal, which I think is kind of fun. So what we have to do is figure out when this curve is going to be at the pole. So when is it going to be at the pole, which is right here? Because, right, if I were to graph this function and the midline is 0, and the period here is 2 pi over b, which is 2 pi over 2, which is pi. I'm going to put pi here, pi over 2. And this would be 2 pi, 3 pi over 2, right? And if I were to graph the sine curve, it's going to go up, then down, and then back again, right? So it's going to be at the pole at pi over 2 and 0, and go up again, down. This is 3 pi over 2, down again, and then the 2 pi. I left the pi's off there. Okay? So one of the leaves, or the rose petals, right, is going to be radially finding the area from 0 to pi over 2, because that's going to be what swept out from 0 to pi over 2. And we know that the petal lengths are 2. So I could find the area one of two ways. I could find the area of one of the leaves or petals and multiply it by 4, which I think is the easier way to go. And you would do this, and then you'd have to use the power reducing identity for sine squared in this case, and you're going to get 2 pi. And then you could also find the area of 4 leaves. And to get 4 leaves, because that's what we have shown here, this is 1 leaf, 2 leaves, 3 leaves, 4 leaves. Okay, so each petal there, or leaf, you'd have to go all the way to 2 pi. All right, and then that would be 1/2 times 0 to 2 pi of r squared d theta. And again, you'd have to use the power reducing formula to integrate sine squared. All right, but I'm not going to do that. I know you can do that. Okay, the last thing we need to discuss is the length of the curve, because the length of the curve, you have a length of the curve in the rectangular coordinates, which is the length equals the integral from a to b of the square root of 1 plus dy dx quantity squared dx. Or if you have a parametric curve, it's the square root of the integral from t1 to t2 of the square root of dx dt quantity squared plus dy dt quantity squared dt. And now when I've got the length of a polar curve, I have to take into account arc length, because that's, r theta. And so it's going to be like r d theta. Okay, so I came up with the proof for this, or the derivation, and you aren't going to be responsible for this, but I wanted to show it to you. And so this video not being so long, I figured I would work it out and show you. And this is how you derive it. Okay, you derive it by finding ds d theta equaling, using Pythagoras, right? little part of the arc length, ds d theta is equal to dx d theta dy d theta, when you square the two, because we have a right angle here. And if you get in close enough, it's locally linear, so you can use Pythagoras. And that's where we came up with this formula here. But you have to remember that x is equal to r cosine theta, y is equal to r sine theta. And since we need dx d theta, we got to use the product rule here. So I went first d second plus second d first. And then to find dy d theta, you have to use the product rule. So you do first d second plus second d first. And then I just put it in a different order because this negative sign, I just kind of wanted it here. So then we have to square each of them, which is a squaring a binomial, which can be a little bit awkward, but not for you BC calculus folks. So you just find this expression. You take this first one and square it, and then 2 times them multiplied together, and then the last one squared. And that's what I got when I squared it. And I did the same thing with dy d theta and squaring it. And then I added them together because that's what we have to do in this nice, lovely square root here. Well, when I add them together, I congregated the ones that had dr d thetas together. See how these have dr d theta squareds? So here we go. I put them together because I knew I was going to factor out what? The dr d theta squareds, right? And then I get cosine squared plus sine squared, which we know is wonderfully 1. And then I congregated or got together the r squared terms and was able to similarly, and I've got a dangling parentheses here, factor out an r squared. And I get another wonderful thing happen, and that's 1. And then I get the actual formula of the arc length of a polar curve, which would be the integral from alpha to beta, because this is only a small piece of the arc length. If I wanted them all, you'd have to sum them all, going from alpha to beta, of the square root of r squared plus dr d theta, quantity squared d theta. And that's the derivation, so that you at least have some understanding of the mathematics behind why it looks like this. And that helps me sometimes when I have to memorize those things. But anyway, so that's the calculus of polar curves. Now, I am posting a summary really quickly onto Moodle, and this is something that I prepared from the AP Calculus Exam Review Guide, and it's a quick summary, and it goes over, our pillars or polars, which I talked about in the last time we got together, and it talks about slope, and it's dy d theta over dx d theta, and they have to use the product rule, okay? And then it talks about the area of inside a polar curve as 1/2 the integral from alpha to beta of r squared over 2 d theta, and of course that equals 1/2 the integral from alpha to beta of r squared d theta. And what's the difference? You're adding up triangles instead of rectangles. Okay. And then if we have a situation where I have 2 different polar curves that I'm finding the area between, I take the triangle of the bigger triangle that I'm sweeping out minus the inner ones that I'm sweeping out. And then this is just a summary of your, different types of polar curves. And let's just review. And then I added this, and I should type it in there, but I will later, I guess. The arc length of a polar curve, which we just derived, which is the L equals the integral from alpha to beta of the square root of r squared plus dr d theta squared d theta. And then one last thing I want to make a distinction between. dy dx is the rate of change of y with respect to x, which is always the slope. This is always the slope, regardless if it's a rectangularly defined curve, if it's a parametrically defined curve, it's a vector defined curve, if it's a polar defined curve, the slope is always dy dx. Okay? Dr d theta, now r is defined as the distance from a point radially out. If I have this polar curve, I'll do my cardioid. R is the distance from the pole, right? No matter where you are. Ha 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 ha. R is the distance from the pole. So this is the rate of change of R with respect to theta. So that is the rate of change of the distance from the pole. And I've seen questions asked like that. dy d theta is the rate of your y variable, which is r cosine theta, or sine theta with respect to theta. So that's just the rate and change of the y point, not in polar curves, but in a rectangular curve. And dx d theta is the rate of change of x with respect to theta, and x is r cosine theta. So that's the rate x is changing with respect to theta. Okay, so these are very different quantities, and it's important to know the difference, and that dy dx is always the slope. Dr d theta is the rate of change of the distance to the pole with respect to theta, and then these are other independent quantities, okay? All right, so I chose to make this video a little bit shorter, with just going over the general basics of the calculus of polar curves, and then maybe tomorrow I'll do a couple of AP examples from the polar curves packet, AP style. So it'll be a second video, and you won't have to be tied to your computer so long. So anyway, have a blessed day, and have fun doing math.